Hey everybody, my name is David. I'm going to be talking about using LAVD in Meta's fleet along with Ryan. And today we're going to be talking about some of the challenges we're facing as we're trying to use a Steamdeck scheduler on a larger machines and servers. So as we've seen before, there's these really specialized S6 layered config and SCX layered schedulers for specific services, but they're difficult to maintain, but they do provide substantial performance gains. Our goal is to provide a scheduling solution for all the rest of the services, and we'll talk about some of the challenges we faced. So one of the issues with running the scheduler everywhere is that we're going to be running into many different types of hardware, but also very different types of workloads such as batched, bursty, or networking. So we'll go through some of the problems. The trend that we're seeing in the fleet is that the machines are getting bigger. So they have more CPUs, they have larger CCX domains, LC domains, and we have to support many different types of topologies. If we take a look at the internals of how LAVD does its queuing and many other static schedulers, is that we would subdivide a DS queue per CCX domain. And generally speaking, there would be some sort of idle CPU selection that would then pick one of these DSQs based on the idleness of the CPUs. And then at the very end, the CPUs would then compete for that task when it's idle and it's trying to run a task from the DSQ. As you can see, the CPUs can also steal tasks from its neighboring domains as well. So one of the issues we ran into is we had one machine that had 50-some plus CPUs sharing a single CCX domain. As you can see, we have now 50 CPUs competing on that single DSQ and hammering on that single DSQ lock. And what this also results in is a lot of task migrations, because since we don't guarantee that the idle CPU selection actually guarantees you to run the CPU selected initially when you push that task in, the CPUs actually just take the task, and then the task tends to migrate a lot more than you would want. Okay, so what happens if we try to subdivide them into what we call these virtual LC domains and try to group these CPUs into smaller clusters? And if you think about the kind of the trade-offs we're making when we're doing this, is that we get less contingent DSQs when we have fewer CPUs per domain. However, we do trade off work conservation because now the tasks have less access or access to less CPUs. So the question is then, what do we pick? Is there sort of an optimal split that you would want to use depending on the hardware? So we did run through a few trials looking at a certain use case, and this certain use case does enjoy L2 cache locality quite a bit. So as we have more CPUs per domain, the CPU migrations happen more and more. So we see the L2 cache rate increase as we have more CPUs per domain, and then the throughput does see regression. Whereas if we move towards fewer CPUs per domain, then we get less L2 cache misses, and then we get our throughput back. And as you can see, the L3 cache miss is with a noise because there's a single L3 domain. However, if we look at latency, as we move towards the lesser extreme, when we have maybe just 2 CPUs per domain, then we start hitting work conservation issues, and then we start seeing latency spikes. So the point of this is to say that there is some middle ground here that we can use to optimize for both work conservation and cache locality. The other thing I want to mention as an aside here is that stealing from across CCX and LC boundaries is generally more expensive. So just like how we were splitting the LC and CCX domains, we can be smart about how and how often we steal tasks between physical CCX and LC domains. And we can generally increase the rate between the virtual LC domains to still maintain good work conservation. I'm going to hand off the talk to Ryan, talk about more of the interesting use cases.
All right, so we've covered 2 out of 4 of the problems that we're including today that we've ran into in production. Problem number 3 is to do with pinned tasks. So we're defining these as tasks that are affinitized to run on a single CPU. And the problem is because LAVD uses these shared DSQs among the cores in a compute domain. The pen task going in the shared queue is a little bit useless for everybody but the one core that can actually run that task. And it does contribute to additional contention and wasted time going through this queue. I'm going to mention a couple different downstream problems from that we ran into. So one, everybody's aware that WhatsApp uses Erlang. That's publicly known. And Erlang, like a lot of language runtime systems, has a worker that's pinned for every core, worker thread. Similar with task scheduling libraries in user space. Now, these Erlang worker threads are especially latency sensitive. They expect sub-millisecond scheduling latencies. And the problem is, if there's anything else scheduled on the same core with the pen task, then now the pen task has to wait at least one full time slice whenever something else is running before it can be scheduled again. Now, LAVD, like a lot of the other SDX schedulers, tends to use somewhat larger time slices than EVDF, for instance. And so we started seeing latency problems here in Erlang, simply because of our time slice size. Now, orthogonal to time slice size, another issue that we ran into was with the load balancing aspect of the system. Now, when we have multiple pen tasks on the same core, in this case, the systing tracing is this one very hot core in the Perfetto trace here that you see the arrow pointing to in the bottom. It turns out that the forced task steal path in LAVD is very sensitive to imbalances in the contention on a given queue, and some of these emergent effects can arise, where in this case, all of the neighbors to the very hot core are losing out in not able to get much work out of the queue compared to all the other CCXs that they're competing with on a relatively large system with more than 100 cores. So the fix here, the solution for these pen task problems is twofold, basically corresponding to the two parts of the problem that I described to you. So to reduce contention on this shared DSQ, we simply take the pen tasks out of it, and we introduce new per CPU DSQs in addition for each core, in addition to having the shared one for the whole compute complex. That eliminates the load balancing problem that I showed you. And then also to deal with the time slice issue, we simply introduce an extra parameter. Not ideal. We don't like to have extra knobs that we have to set for every scheduler. But this extra parameter allows us to specify an alternative time slice size to use whenever you happen to be cohabitating on a core with another pen task. Use the smaller time slice. So you don't get in its way as much, simply because these pen tasks are somewhat fragile in that, unlike other tasks, they can't simply jump over to another idle CPU, and they're not able to run again until their home CPU is ready. Question?
Yeah, how do you consume from the per CPU DSQ versus the shared?
Yes, great question. As soon as we have these two levels, now we're in this kind of multi-tier queuing situation. So we consume by simply peaking at both of them. And this is helped by having a new patch to the kernel that enables lock-free peaking at multiple queues. So we can peak both, pick the lowest V time one. OK, and with that in place, our load balancing problems are fixed, and all the cores are somewhat happy and not visibly underutilized. All right. That's problem 3. One more problem for this presentation. So this is to do with IRQ-heavy workloads. In this case, this is a caching service that is servicing millions of requests per second and has an unusually high percentage of time spent in interrupt handling. So in this case, a little under 50% of the cores are beset with network card interrupts, and more than around 25% of total CPU time is spent in interrupt handling. So it's really important that the scheduler take that into account and handle it correctly. LAVD was not initially taking it into account, so if you ran for 5 milliseconds, you would be charged for the full wall clock time, even if half of it was blown away by interrupts. So we landed a patch that simply fixes the accounting, so you essentially get reimbursed your time back, vis-a-vis fairness with other tasks running on the same core, or vis-a-vis a CPU max limit that you might be up against. So that fixed that problem, and we have an outstanding patch to add some new load balancing logic, which is more tentative, but tries to model the capacity and responsiveness of different cores, somewhat analogous to this concept of big versus little cores, but in this case, cores that are beset by a high interrupt load versus other cores that are not. And then LAVD has already put all this logic into identifying latency criticality. The latency critical tasks that you identify, you want to prioritize to the higher capacity cores that are not beset with interrupt storms. All right, so there we are. 4 different problems and 4 different solutions. One cross-cutting issue that we don't have time to talk about today, especially at the very end of the day, is all of these, almost every talk we've talked about today has to, implicitly in the background, depends on being able to benchmark and measure schedulers, to trace their behavior, to reproduce problems when you see them. And that, for us deploying new schedulers in production, has been a big part of the story, is how do we test schedulers ahead of time? How do we find problems in production? How do we then build reproducers for those problems, especially so we can collaborate with the open source community, who we can't just give access to first-party services, right? So we're getting somewhat better at that over time, and I think it's a talk of its own to get into that in the future, fast and repeatable reproducers for problems. So the list we gave today of problems was non-exhaustive. We certainly found other problems in production, but due to time, we will leave it at that and give you some ideas for things to ask us about. All right, any questions? Maybe while these, oh, yeah.
Yeah, so you were saying in the beginning it's sort of like a general purpose scheduler, but so where do the priorities actually come into play? And how does it relate to the CPUs that get pinned?
Sorry, the priorities meaning like the latency criticality and the virtual deadlines, or?
Yeah, because like you mentioned, like you have like a high importance workload or whatever. So how does that come into play if it's just like a general purpose scheduler?
Yeah, I guess there's different degrees of general purpose. So like eVDF ships to the whole world, has to work on cell phones, has to work in a million different contexts. So we are specializing somewhat to the set, the meta fleet of services running in the data center. And but within that, there's a fair amount of variation. And within an individual workload, there's a fair amount of variation where some threads are quite important and are latency critical. And then other threads are background worker threads of various kinds. We already had the presentation from Patrick and others on the AI applications where you want to use layered to separate these different categories. But that layered methodology requires a human to go in and say threads that are named foobar are extra important. In LAVD's case, it's using its own algorithm, which was alluded to by the equation in some of Chang-Wu's slides, to estimate latency criticality, and then those have an earlier virtual deadline. Now this pinned thing doesn't directly correlate with LAVD's estimation of criticality. But we're putting in these extra heuristics to treat pinned tasks as probably more latency critical. It's one more hint, it's one more Bayesian factor for us.
Cool.
Hey, you guys mentioned the IRQ time scale as being pretty painful for determining which cores can accept work, right? Do you guys ever try like threading those interrupts? I know that's like an option. I don't know if it will make things worse.
Do you know that one? I think we're both drawing a blank.
Yeah, where you expose the software IRQ cost to the scheduler.
So this is where they're scheduled over to user space.
Yeah, we've looked at that just a little bit, but it does have some substantial overheads that we found for a bunch of workloads, so it's hard to apply generally. And again, that's part of the challenge here.
So thank you for the great talk. And I'm just wondering about, so I understand that LAVD has initially designed to optimize for Steamdeck, right? And now you are trying to make that also optimized for metadata centers or data centers in general. Is there some kind of were there any kind of conflict about some kind of optimization decisions? For example, you could make some changes on LAVD that can benefit on Meta's data center, but making some regression to Steamdeck, and also are you now totally aligned on pushing the two goals together?
Yeah, Chang-Wu can help answer that to say that, like, have we pushed any patches that have then caused problems on Steamdeck? Because we're not testing on Steamdeck. I have one, and I've been meaning to, but I haven't. What we've seen so far on our end is more just things that are not so applicable to us. We don't have big little, so it's not applicable. But Chang-Wu? Or David?
Honestly, I do not have a good answer because still the experiment is going on, but so far the changes for the matter for the server workload is either one of two, irrelevant to the Steamdeck or helpful to the Steamdeck. So far I think it is okay. So we can actually live together. So who knows in 2 years.
And LAVD does offer many different configurations and options that we can use, like performance modes that wouldn't take into account core compaction and big little, and so we can kind of you can work around that with different modes of operation as well.
Too many knobs. Yeah. Well, I think we're embodying deadline scheduling here because we're finishing right on time in spite of having certain points where we were delayed.